This is another really short tutorial on the difference in the properties of ionic compounds versus covalent compounds. So the difference between the properties of most compounds depends on the intermolecular forces and general intermolecular attractions. And what is that? Pay attention to the inter part. That is the attractions between separate molecules. Okay, so a lot of the properties that we're going to talk about, hardness, brittleness, melting point, boiling point, these are all properties that they're not chemical properties, and they do not break any chemical bonds when testing these properties. They simply affect the attractions, the intermolecular attractions between molecules. So ionic compounds, let's think about what they're composed of. They're composed of charged ions that are held very, very close together because of the strong electrostatic attraction between oppositely charged ions. And there are no discrete molecules. You can't go in and pluck out, let's say, for example, one NaCl unit because it's a big three-dimensional network. And so they are always solids because of this tight packing, and they are always crystalline solids, okay? They have a very highly ordered structure, a repeating structure over and over, and so that gives rise to a crystal. They're very hard and brittle for the same type of reason. Imagine trying to take a hammer and separate all these individual ions. It would take quite a bit of force. That's the crystal lattice force that we learned about. And so they tend to be hard and brittle. The strength of the crystal lattice also gives rise to very high melting and boiling points. As a matter of fact, the melting points of most ionic compounds are significantly higher than 300 degrees Celsius. Some of them are up in the thousands. Most ionic compounds dissolve in water. Remember the phrase I told you earlier, like dissolves like? That means polar compounds dissolve in polar solvents. Nonpolar substances dissolve in nonpolar solvents. Like dissolves like. So water is polar, okay? It contains polar covalent bonds, and ionic compounds are very polar, extremely polar. And so most ionic compounds will dissolve in water. Ionic compounds conduct electricity, but only when the ions can move. So ionic compounds do not conduct electricity in the solid state because the individual ions are packed so tightly they cannot move about. Remember now what electricity is. It's the free flow of electrons. So in order to conduct electricity, those electrons need to be able to move about. So if you take an ionic compound and melt it or dissolve it in water, you now have freely moving ions, and both of these conduct electricity. So for example, most people don't realize this, but pure water doesn't conduct electricity. It's just that we almost never have pure water because it dissolves so many different things. So all of the water that you run into outside or even in your home already has quite a bit dissolved in it, and that's why it does conduct electricity. But in the pure form, it does not. Pure solid ionic compound does not conduct electricity, but again, if you melt it or dissolve it, it will conduct electricity. Some of the common ionic compounds that we deal with day to day in our lives: sodium chloride, table salt, potassium chloride. You may be aware that in particular in cases when people have high blood pressure, they're told to stay away from sodium. And so some of them will use an alternate to table salt, which is potassium chloride. I guess they call that light salt. Calcium chloride is what we put on our sidewalks when they're icy or snowy to help keep the ice in liquid form. Calcium carbonate is chalk. And a lot of ionic compounds ammonium-based in fertilizers. Now, covalent compounds are all over the board as far as their properties. Whereas ionic compounds are always solids, covalent compounds can be any of the three states of matter, gases, liquids, or solids. Think of carbon dioxide gas, water is a liquid, charcoal briquettes are solid, and those are all covalently bonded. So their properties are all over the board too. And again, the properties depend primarily on intermolecular forces. Again, that's the attraction that exists in between molecules. Okay. Obviously, an ionic compound has very, very strong intermolecular forces because of those oppositely charged ions. The intermolecular force in a covalent compound varies dramatically depending on what the compound is. But in general, we can say that covalent compounds have lower melting and boiling points. You can think of some covalent compounds with extremely low melting points. Think of wax, for example. Actually, anything that's in the liquid state of matter has already melted at room temperature. And then we have some covalent compounds that we can think of as pretty high melting. So, for example, think of sugar. It'll melt / burn at a high enough temperature, but it's not like wax or already a liquid. It's worth emphasizing again that when you melt something or boil something, you do not break any chemical bonds, okay? You don't change the nature of the substance. You just loosen the intermolecular attractions. That's all you're doing when you're melting or boiling something. Covalent compounds are poor or non-electrical conductors. There aren't any charged particles. You will see that there are some exceptions. When we learn more about acids and bases, we'll learn that they can make some charged substances, hydrogen ion and hydroxide, and those can conduct some electricity. But in general, a regular covalent compound does not conduct electricity. The solubility of a covalent compound is all over the board. It depends completely on polarity. So we have some polar covalent molecules that'll dissolve well in water, and we have some nonpolar ones that don't dissolve very well in water. All right, so just many examples of covalent compound gases and liquids. Okay, all the gases in the air are covalently bonded. Here's a good old caffeine. That's actually a solid. Okay, water is a real common covalent compound. That's a liquid. So really all states of matter, tons and tons of different types of covalent. There is one final class of covalently bonded compounds that I would like to mention. They are called covalent network solids. They are covalently bonded. They are made up of atoms that share electrons, but they're unique in that each atom in the covalent network solid is interconnected in all three directions in space. And so they had to stop at some place, so don't look at the terminal atoms. But if you look at every atom in the middle, they each have a bond going in all directions. And so it ends up being a 3D network, and it ends up having some properties similar to an ionic. They're very, very strong. They're always solids. They're very brittle, okay? They're very tightly packed, okay? And they're some of the strongest materials known to mankind. And they tend to be carbon-based, okay? So a diamond is an example of a covalent network solid. Or they can be silicon-based. Okay, both carbon and silicon can make 4 bonds each. Things like sand is silicon dioxide, okay? And that's a covalent network solid. Very, very strong solid. So for a quick summary of some of the differences between ionic and covalent compounds, we haven't talked much about metals, but just it's nice to see a comparison. Look this chart over, make sure that you know it, and that's it for this presentation.